The objective of this challenge was to build a two-dimensional arrangement with a guitar string in a specific weight. We had to calculate the weight necessary to generate the tension needed on a guitar string to produce a specific frequency, as well as the necessary length of the string to obtain both theoretical and experimental frequencies.
To find the linear density of the string, we first have to find its mass and its length. To do this, we went to the chemistry lab and weighed the string, which gave us a mass of 0.001254 kilograms, and then with a flexometer, it gave us a length of 1.02 meters. Then its linear density is mass over length, which gave us a linear density of 0.001231 kilograms per meter.
To obtain a theoretical tension, we first set a frequency to 400 Hz. This is the frequency that we wanted to obtain. Then we simply plugged it into the formula. Frequency equals nodes times velocity over 2L, and then we just solved for the tension. Then when we got the tension, we divided by 9.81 to get the mass. We divided by 9.81 because when we did a free body diagram, we saw that tension was equal to mass times gravity. Therefore, that's why we did that. So the tension that we got was 49.24 newtons, and then when we divided by gravity, which is 9.81, we got a mass of 5.02 kilograms.
Now what we want to do is change 400 Hz to 500 Hz by changing the length of the string. We once again use the formula of frequency is equal to 1/2 length times the square root of tension over linear density. And now placing 500 Hz in the frequency, and now solving for L using the same tension and the same linear density as before. We got that the length we needed to obtain in order to make 500 Hz of frequency was 20 centimeters. So we had to reduce the length from 25 centimeters to 20 centimeters, and we did this by using a pair of tweezers and holding pressure on the string at exactly 20 centimeters.
In experiment 1, we got a theoretical value of 400 Hz, while an experimental value of 415 Hz, which gave us a percentage error of 3.775%.
In experiment 2, we set the frequency to 500 Hz, and our experimental value was of 484 Hz. This gave us a relative error of 3.2%.
We achieved successfully the objective of this challenge because when we put 5 kilograms to the end of the string, we obtained a frequency of 390 Hz. And when we cut the string with our finger into a shorter length, we got a frequency of 484 Hz, which is higher.
We were able to complete our objective since we obtained the theoretical frequency as well as the experimental frequency. We obtained an error of 3.75% on experiment number 1 and 3.2% on our second experiment. A source of error might have been the application we used to measure the frequency, since we realized that even when using 3 devices at the same time, they didn't all agree on the frequency being emitted. We could have used a frequency sensor specifically used to obtain such sounds and frequencies. The second experiment is very evident on a real-life situation. It's how string instruments are able to produce such a variety of notes and are able to play melodies. A violin, just as well as guitars, use the length of the string in order to be tuned and accurate on the notes for the melody. As we observed in some parts of the video, we did have to do our experiments on 2 different occasions various times. This was in order to obtain a frequency around 440 Hz, and we realized that the more weight, the easier it was to reach such frequency, hence showing adjustments we made on our trials.